This is an autonomous differential equation. The right-hand side is an f of y. We could use all the techniques from chapter 1 to think about this if we wanted to, including slope fields and phase lines. But we're after a symbolic understanding of a couple things in this problem. And so I had you use Mathematica to solve it. If you use d-solve value to solve this differential equation, you should get this kind of expression right here. You certainly could have worked with this, but you also can make it a little simpler. This is what I usually do by dividing the top and the bottom by e to the t. That'll cancel the e to the t in the top. It'll cancel this e to the t in the bottom. You might say, well, I have e to the negative t times that, but that's actually a little bit better if you think of multiplying that entire thing in parentheses by e to the negative t. And that's what I've got here. It's kind of the simplest way to write the solution of this generic initial value problem. But the first problem here, part A, was to verify that if you define a new function to be a horizontal translation of this, I called it fancy phi of t, to be a horizontal translation of this function, that it also solves the differential equation, not the same initial value problem, but the differential equation. There's two ways this can be verified. One is much quicker, though more abstract than the other. Let's do it the way you probably did first. You probably plugged in t equals t minus h. In other words, replace t with t minus h. I'll do it with my formula here, like this. And you want to differentiate that and show it solves the differential equation. It is kind of a pain. So we need to verify that the left-hand side equals the right-hand side when we simplify. Okay? It's worthwhile going through some painful experiences sometimes for the purpose of knowing you can do it, if nothing else. So this fraction, I can use the quotient rule. Low d high means the bottom times the derivative of the top will be 0, since the top is a constant, minus high d low, take the derivative of the bottom here. The y0 differentiates to 0. This thing is a constant times e to this power, which is the same as e to this power. By distributing the minus sign through, I'll need the chain rule. I'll get an extra factor of -1 because of the negative in front of the t. The 1 minus y naught can just stay there. And maybe I'll go back to using parentheses here, get an extra factor of -1, divided by the square of this whole thing, and you do not have to square this whole thing. Just write it as a square. Maybe you tried squaring it, but you don't really have to. Simplify a little bit is probably worthwhile. These two negative signs would cancel to give you a positive sign, because I could think of the negative y naught as coming through the parentheses here. The 0 doesn't affect anything. Looks like this simplifies to y naught, 1 minus y naught, e to the negative t minus h, all over this thing in the bottom squared. That's about as simple as it gets, it seems, for the right-hand side, or the left-hand side. Now the right-hand side of the differential equation is y times, in parentheses, 1 minus y. Replace y with the function, and then replace the function with its formula, this thing, and simplify. Y naught over y naught plus 1 minus y naught e to the negative t minus h. That's the function. Then I'm doing 1 minus the function in the parentheses here. And I'd want to get a common denominator equal to this crazy thing here. Replace the 1 with a y naught plus 1 minus y naught e to the negative, in parentheses, t minus h over itself. And then subtract those fractions. The y naughts would cancel, right? You got to subtract the numerators. The y naught here and the y naught there will cancel. Yeah, we're almost done. What's left over gets multiplied by this thing and will give you this. You will get the same thing because you got a y naught and a 1 minus y naught on top. And this e to the negative in parentheses t minus h. And on the bottom, you've got the exact same thing in both fractions. So you multiply it by itself, you square it. So it does simplify to the same thing. We verified the left-hand side equals right-hand side, no matter what t is. Yes, not pleasant, but doable if you're careful. There's a quicker way to actually do this. It's worthwhile to go through the less quick way to realize maybe it'd be nice to have a better way to do it. And maybe this better way would apply no matter what your right-hand side function is, as long as it's a function of y. And that's the point, actually. Think of this abstractly. This equation right here. Abstractly. In other words, don't use this formula. Just use this formula. How? So fancy phi prime of t, if I use this abstract formula, I guess I got to differentiate ordinary phi. And I've got a t minus h instead of t in there. I guess I got to use the chain rule, but it's a trivial application of the chain rule because the derivative of t minus h with respect to t is just 1. So I get this ordinary phi function prime of t minus h times 1. But then what do you do with that? If I don't use the formula for phi sub y naught, how can I possibly do anything with this? I know phi of t satisfies this differential equation. That derivative that I just wrote down will equal what I get when I plug this thing into the right-hand side in place of y. But you don't have to plug it into here. You can just plug it into f. This equals f of phi sub y naught of t minus h. Why? Because phi sub y naught solves the differential equation. When you plug it into the left-hand side and in the right-hand side, you get the same thing no matter what the input is, even if the input is t minus h. Is that it? That actually is essentially it, because this thing, phi sub y naught of t minus h, is the same as fancy phi of t. By definition of the function fancy phi. Left-hand side equals right-hand side. Done. I don't even need the formula for f. That's very powerful. That's very powerful. I can explain. This is very powerful. What this is essentially doing is it's showing that for autonomous differential equations, I didn't even use that expression there. I just used the fact that it was autonomous. dy dt equals f of y. And defined a new function based on an old function that was a solution, assumed to be a solution. It's a horizontal translation of that old function. If h is positive, it's a translation to the right. If h is negative, it's a translation to the left. With autonomous equations, you get a new solution. It's the left-hand side ultimately equals the right-hand side when you plug in this new function in place of y. That's a symbolic confirmation of what we already knew from vector fields for this kind of thing. We know the vector field for this kind of differential equation is constant along horizontal lines. It also happens to have two equilibrium solutions at 0 and 1. Because it's constant along horizontal lines, if you translate a solution to the right or left, you'll get another solution. It'll still follow the vector field. We already knew that. This is this abstract symbolic confirmation of that. I'm not saying this is easy because it's abstract, but once you see it, if you think about each step, you can understand the reasons. That's just the derivative of phi by its definition, fancy phi, with a chain rule, multiplied by 1 because 1 is the derivative of t minus h. And non-fancy phi sub y0 solves the differential equation, so left-hand side equals right-hand side. It doesn't matter what the input is. It doesn't matter if it's t minus h instead of t. But by definition, this thing inside F is what fancy phi is. The other question was to what's the initial condition? Just plug in t equals 0. That's all you have to do. That's the easier part when you know what to do. The initial condition fancy phi of 0 is in the abstract going to be the original phi function sub y0 of negative h. Replace t with 0. And for this example, replace t with 0 here. You're going to get, in this form at least, y naught over y naught plus 1 minus y naught e to the, it would be positive h power if you write it in the way I did. You had, if you didn't write it in this way, if you had the e to the t up there and e to the t in the bottom, then t minus h when t is 0 would become negative h. Okay, so this is one form of the initial value at t equals 0. Do notice there's also another initial value, you might say, fancy phi of h equals phi sub y naught of h minus h is 0, but that's y naught. That's not an initial condition, you might argue, because I'm not starting at time 0, I'm starting at time h. But that could be thought of as an initial value if you imagine starting at time h, which, you know, in physical problems, when you're applying math, it's just convenient to start at time 0, but you could start the clock at some other time, whatever you declare to be the starting time.